So what I'm playing around with in terms of doing the lecture on this online platform is to try and make it more interactive because we don't have a face-to-face. So we're going to see if this works. If it goes haywire, then I will make up for it. And let's get started. Also, Mr. Marcel Denny is in the chat, so if you guys have any questions, he'll be there to answer things as we go along. All right, so let's go. So for today's lecture, we are going to get a reintroduction to coordination complexes. We're going to tackle calculating oxidation states. We're going to look at how to count the electrons and then jumping into isomers. And that's quite a lot of things to do in one session, but if we're really good and we can get through it, we might start with how to name these compounds. And then if whether or not we get to naming, I'll have a question and answer session and any other business that might come up. So in terms of any other business, first thing is that the library has photocopied several chapters of textbook Chemistry 3 by Burroughs. It's a textbook that I've been following in doing inorganic lectures. So chapters 25, 26, 27, 28 are available on Orville in their entirety. You guys have access to that and you guys can use it. We've also copied the chapters for physical chemistry and kinetics and organic. Some organic is up and more organic chemistry notes will be coming later for those of you guys who like it. All right, so let's jump into it. So let's start off with a question. So I've given you a question on the board and we're going to see if we remember anything from last month. And I'll send up a poll question now. All right, guys, I'll give you guys another minute to work on this. Don't worry, I can't see who's responding to what. So just answer to your heart's content and see how we do. All right, 10 more seconds. 3, 2, and 1. All right, so let's see what we have. So majority of the answers are for A and C. So we have a tie with only 6 people showing 5 people choosing B and 4 people choosing D and 56 people not responding. All right, so let's see how we approach this. So it's manganese cations. The first thing we have to know is the electron state for manganese. So you should remember now that it will be AR, 3D comes first, and it'll be 5, 4s, 2. So the question is asking us for the manganese for a cation, which means that we would have lost 4 electrons. So if we lose 4 electrons, The first one will come on. This is very interesting. Will come from the 2. So we lose 2 there, and then we will lose 2 from the D's, right? So 5 minus 2 equals 3. So the correct answer would be C, AR 3D 3. Okay. Does that make sense to you guys? Why the answer is AR 3D 3? For 4. So we'll have more. So we'll have more oxidation as we go along. All right. So let's jump. Oh, another question. So in the coordination, so the second question is in coordination chemistry, the donor atom of a ligand is. Okay, here we go. A, B, C, or D. All right, from most of your answers, everyone was picking D, and I also saw it in the chat. So right, the donor atom of a ligand, and let's use a generic ligand as an example. We'll use ammonia, where the donor atom is nitrogen and ammonia. It's not a Lewis acid. Remember, Lewis acid accepts electrons. That ligands are Lewis bases, right? It's not the central metal ion. That will be the Lewis acid is a central metal ion. The choice C says the atom of the ligand that accepts an electron pair from the metal. No. So the correct answer would be D. The atom of the ligand that shares an electron pair with the metal. If we all are on that, we remember stuff that we've done from last time around, and we're ready to jump into new content. But we'll still do a little bit of revision as we go along for those of you who may still need some catching up. All right, so in this lecture, we're going to continue on our discussion on coordination compounds. And so if you recall, a coordination compound is a natural substance in which at least one ion is present as a complex ion. So I'm showing you on the left is this cobalt coordination compound that has 6 water molecules attached to it and nitro group as a counter ion. All right, so remember anything in the brackets is a complex ion and the counter ion resides on the outside. So if we wanted to break this down, we could actually say, okay, this is made up of a complex ion. So my complex ion is going to be cobalt with 6 water molecules around it, right? And then my counter ion will be NO2. So NO2 is my counter ion, and this is my complex ion. So something that's missing here. So it's a compound, which means it's made up of a cation and an anion. So therefore, We already know that NO3, sorry about that, is a -1 charge, and there are two of those, which means if there's two of those, the charge on my complex ion must be +2. All right. So the next thing we want to know is, so we know for the first part of this question, we know our counter ion here is NO3. So what's the geometry of this compound, and what do we use to get geometry? And to figure out the geometry, we have to figure out recall what is the coordination number. So the coordination number is a number of points of attachment or number of ligands that are surrounding the metal ion. So for those of us who can look at this, we can look here and see, okay, here's a COH2O6. There's 6 water ligands here, therefore the coordination number is 6. And we can even go even further and draw that out. So we have CO, water, and I'm binding, look, through the oxygen, right? Because that is where I have available electrons in order to make a bond with my metal center. And now we can see 1, 2, 3, 4, 5, 6. And so therefore, the structure is, hold on, what happened here? I'm not sure what happened, guys, but there seems to be some technical difficulties. All right, let's go through that again. All right, so we had broken down that this was a complex ion. Okay. All right. This is minus, and then we had drawn it out. All right, so that will be what our structures look like. Again, our counter ion will be nitrate, which will be NO3 minus. Our geometry would be octahedral, and our coordination number is 6. All right, let's try another example. So here is silver diamine complex. So in this example, we also have silver, and if you look at it, everything here is in square brackets, and you'll notice that there is no counter ion, which means this is a complex cation. So here it's silver with 2 ammonia ligands around it. So right away I know that my coordination number is 2. So if my coordination number is 2, that means that my geometry has to be linear. So my geometry is linear, and I have no counter ions in this example. But if I were to put a counter ion here, Can anyone think of an appropriate counter ion that I could use in order to balance this equation, in order to balance the charges here? NO3, right, Michaela? So it's a positive charge that's on the complex, which means I need to have something that has a minus charge on it. So I could use something that's a -1, right? So if I were to use NO3 again, I could make the nitrate salt. I could use I could use sulfate, but in that way I'd have to balance the charge because sulfate is 2-. So therefore I'd have to have 2 of this if I wanted to use the sulfate. That's an ugly 2. If I wanted to then use sulfate as my counter ion. Right. Yes, hydroxide could work, though in presence of silver, we might get another type of reaction. All right, chloride also could work. Good job. All right, what will not be appropriate here is something else that was positively charged because we're trying to balance a positive charge. Okay, so let's do, Is anybody else not seeing the drawing? Oh, okay. That would be an internet issue, and I apologize. But if you have access to, when these are recorded, you'll be able to see my drawings and all of that stuff. All right, we just have to keep working with this. All right, so let's look at another example of this. Are you guys getting the hang of this? Okay. All right. Awesome. So here's another one. So this now is potassium, and here's another complex. So by now we should realize wherever we see parentheses, that means that is our complex ion. And whatever is on the outside is our counter ion. So in the little box here, it mentions that there are 4 potassium counter ions, each with a +1 charge. The charge on the complex ion must be -4. But if we're following along, we should have been able to appreciate that from before, right? So now if we're going to look at this compound now to try and figure out the coordination number of the geometry and the ion, if you look at it right away, you can see that it has 6 cyanides. So therefore the coordination right away has to be 6. If the coordination number is 6, by now you should appreciate that the geometry is going to be octahedral, right? So we should be able to now be comfortable drawing manganese. And remember, we always show our stereochemistry when we're drawing, right? Because we're trying to represent a 3-dimensional figure in a 2-dimensional space. And in this drawing, I'm showing that my cyanide is binding through carbon. So if you guys go back and draw the Lewis structure of cyanide, you'll see the negative charge resides on carbon in the structure. So again, my coordination number here is 6. My geometry again is octahedral. And my counter ion here is going to be potassium, and I have 4 potassiums. Notice that, okay, that my potassium now goes on the left-hand side because it is my cation. And therefore my complex is now, my manganese complex is now my anion. Okay. We removed, okay, all right. So if we think about it here, there's 4 potassium ions on the outside, which means the overall charge for this manganese complex here has to be -4. Up to now, all the examples we have seen have used neutral ligand, mainly ammonia. And with a neutral ligand like ammonia, it doesn't have a charge. So therefore, the charge, I'm not drawing right now, the charge on the complex So therefore, the charges on the complex that's on the complex of fire has equal the charge of the ion, but manganese with cyanide ligands around it is a special case. So here now we have, so let's look at this further. And the question asks, what is the oxidation state of manganese in this complex? So the overall charge is -4, and I have cyanide anion. And the cyanide anions each have a minus charge. So when we're calculating the oxidation state of these complex ions, it's very similar to what we were doing before when we were calculating oxidation of simple organic molecules or simple main group molecules like phosphate and sodium chloride and sulfate. Same principle. The difference here is that we're using ligands, and in some cases, our ligands may not be charged, and in some cases, the ligands might be new to us, but it's the same principle. So in this example, we know that the charge of the complex is equal to the oxidation state of the metal plus the charge of the ligands. All right, so let's try that out then. So using this equation at the bottom, the charge of the complex we know is 4 minus or -4. So -4 is equal to oxidation state of metal, which we don't know, so we'll just put manganese for now, plus the charge of the ligand. As we said before, cyanide is a -1 anion, and there are 6 of those. Therefore, the charge on my ligand is going to be 6 times -1. All right? I can solve for the oxidation state of manganese. So it'll be -4 plus 6 is equal to Mn. So plus 2 is equal to the oxidation state of manganese. All right. Do we all see that? All right. So it's pretty, all right, great. Okay. And don't worry, we'll be practicing more oxidation states as we go along. So in general, neutral ligands have 0 charge and they do not contribute to the charge of the complex. However, anionic ligands or charged ligands, so you can have positively charged ligands binding to a metal center. But in this class, we're only going to focus on neutral ligands and anionic ligands, the ones that have a negative charge, right? And when charged ligands bind to a complex or bind to a metal, it's going to contribute to the charge of the complex. And so the best way to do all this stuff is not to watch me, but is to practice. So I'm going to give you guys 4 minutes of practice. There are 3 examples presented, and you guys can try working on it. The first 2 is similar to what we've done before. C is a little bit challenging, but I've shown you. N is ethylene diamine, and I'm showing you the ligand here. And pyridine is also shown here, and they are neutral ligands. Oxidation state is necessary to find because by knowing the oxidation state of the metal center, it tells a lot about how that metal is going to behave. We can tell what the geometry is going to be like. We can tell what type of ligands it wants to interact with. So oxidation states basically are a part of our toolbox to let us understand the chemistry of these transition metals. All right, I'm going to be quiet for two minutes, and I want you guys to try these. All right, so go for it. Also, I've unmuted your guys' mic, so if somebody wants to ask a question, just raise your hands and I'll take a audio question. Yes, pyridine is neutral. So neutral ligands are anything you can basically buy in a bottle, and you can definitely buy a bottle of pyridine and it will stay on the shelf for quite a while and it has a very distinct smell. All right. I will go through the practice questions. If you want to, you can respond to them in the chat, or you can keep your answers to see as check them as we go through them together as a class. Or if you want to unmute your mic, you can unmute your mic and you can share with us. All right. Nadisha has already provided us with 3 answers. Let's check them. That's what she got. All right. Let's see. All right. So let's look at these. There will be no repeat lecture tomorrow. Tomorrow will be office hours if you guys have any questions from 8 to 9. All right, so it seems as though you guys are really getting these, so therefore we'll just go through them very quickly. All right, so for the first one, in calculating the oxidation state, so we're going to do nickel complex first. Again, we now can separate the 2 bromides away and we can go down to the complex itself. And we can see that the overall charge of the complex is +2 because there are 2 bromide anions. Therefore, because these are neutral, give me a second. Okay, because these are neutral ligands, we can know right away if you look at the complex that this is going to be nickel 2 plus, right? Because ammonias are going to be 0. So if you want to do the long way around, you can say the charge in the complex, which is -2, right, is equal to the charge of the metal, which is nickel, which we don't know, plus the charge. Ammonia is 0. Therefore, it's going to be 6 times 0, which is 0, is equal to -2. So therefore, nickel must be +2. All right. For the other one, now we're going to have our complex ion is now an anion, right? And we're now cesium is our common to iron. We have 3 cesium ions, which means the overall charge of the complex is going to be +3. I mean -3. All right, Maisha, where did we lose you? For the first question or the second one? All right. How did it become +2? So if we go back again, and let's just clear. All right. Let's go back to the first one slowly. All right. So if we look at this complex, we see that there's nickel in square brackets with 6 ammonia ligands around it and 2 bromides. Bromine is in group 7, so therefore if it's 2 bromide ions, each one of these should have a -1 charge. So 2 of them is going to have -2. So therefore the charge inside the bracket has to be +2 because this is a compound and it's going to be neutral. So therefore the charge, so we know that the overall charge of this is going to be +2, which is going to equal to, from the equation we saw before, the charge of complex is equal to the charge of the metal, the oxidation state of the metal plus this charge of the ligands. Oxidation state of nickel, ammonia is neutral, which means doesn't have a charge. So therefore, we have 5 of those. So it's going to be 5 times 0. So therefore, +2 is equal to X. So therefore, nickel has a charge of +2 in this molecule. For the third one, cesium is a group 1 cation, so therefore there are 3 of these, so these are going to be +3 charges. So therefore, the overall charge of the ferrate, so iron with its 6 cyanides around it, is going to be -3, right? Same principle as before, so -3 is equal to X, where X is now our iron, plus 6 times -1, because we said before that each cyanide is -1, right? Each cyanide is going to be -1. So therefore, it will be -3 is equal to X minus 6. 3 minus 6 is equal to X. Sorry, -3 minus 6 is equal to X. X should be equal to +3. Sorry. X equals +3. So in this case, iron 3. All right, in our last example, this is not a salt, it's not a compound, it's a complex molecule, right? There's no charge on it, which means all the charges are taken care of by the ligand. In this example, we have chromium in the center, and our ligands are chlorine. We have 3 chloride ligands, we have an ethylene diamine ligand, and we have a pyridine. So these ethylene diamine ligands are neutral, as is pyridine. So they'll have 0 charge. So they'll be 0 and 0. But chlorides will each have a -1 charge. So therefore, the overall charge of this molecule is 0. So 0 is going to equal to the charge of our metal, or the oxidation state of our metal, which we don't know, so we're going to call that X, plus the charge on our anionic ligands, the chlorides, it's going to be 3 times -1 plus 0 plus 0, right? And so if we solve for this, we find that X is equal to +3. So we have chromium 3 plus. So the secret to all of this and in order to oxidation state is just to practice, 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 practice. And one thing you have to do in this course is a lot of oxidation state. Um, um, the overall charge is 0 because the charge on the chromium is +3, and the charge in the chlorides are or 3 minus complete. When they form a complex together, they cancel the charge. The overall charge is 0. So you don't have, in the case of like nickel, where you have the 6 ammonia around it, and they don't have any charge. Therefore, when you add the +2 charge of nickel plus the 0 charge of the ammonia, the overall charge of complex becomes +2. So therefore, you have to have a counter ion with it. In the case of this chromium complex here, the ligands on the metal center satisfy the charge, and so the overall charge is going to be equal to 0. All right. So now that we've calculated oxidation state, another key thing to know in these complexes are d electron count. And so the further you go, if you do more inorganic chemistry, especially for the D block, people always refer to metals based off how many d electrons they have, the oxidation state and the d electrons, because it tells you a lot about how this metal is going to behave and the type of chemistry that will partake in, and even sometimes you can even learn about the geometry of the compound. All right, so again, from the first example, we saw that we had nickel 2 plus, we had iron 3 plus, and we had chromium 3 plus. All right, so the question becomes, how many d electrons do we have once we've taken into account the oxidation state of the metal? Because if you think about it, if our metal ions are in the +2 on the +3 oxidation state, it means that they have lost electrons, right? So if we go back to the neutral, so if we look at the neutral nickel atom, it's going to be argon 3d8 4s2, which means that if nickel lost 2 electrons, if it's +2, it means it lost 2 electrons. Therefore, I'm going to have 8 d electrons left on my nickel. So therefore, this complex is a D8 complex because it has 8 d electrons. We can do the same thing with this iron complex here. So here's iron, iron 3 plus, and the neutral iron is Ar 3d6 4s2. We've lost 3 electrons, so the first 2 are going to come from the 4s, and then we're going to take 1 from the D, leaving 5 electrons left, so therefore this is going to be D5. The last one, chromium, and please remember that chromium doesn't have a standard electron configuration that has a half-filled d orbitals and half-filled s orbitals. So it's 3d5 4s1. If we lost 3 electrons because it's chromium 3 plus, 1 electron comes from the 4s orbitals and 2 is going to come from the 5. So 5 minus 2, that leaves us, let's see, 3, sorry. So that's going to be a D3 system. All right, did we get that? Is that a no? I'm not seeing any responses. Ah, great. And that's the D electron counts. As I said before, they're pretty important. We're going to see more of it as we go through the semester. All right.
Yes.
So another way of doing D electron counts is to just, I will do it again. Is to look at another equation for it is the number of d electrons is equal to the group number minus oxidation state of the metal. So therefore, let's look back at your chromium complex and a different way of how to get to the same answer. Okay.
Dr. Stevenson.
So a different way to get to the same
Dr.
answer. If you
Stevenson.
can't see what's happening on my slide as I'm annotating them, please just refresh your browser. It's probably an internet issue. If you want to say something, just raise your hand and ask a question and unmute your mic and you can ask. Oh, I can't hear it. I'm not hearing anything. Hello? Mm. Okay, I'm not hearing you guys, so I'm not sure what's going on there. So you guys can try writing. You can try raising your hands to see if I should be able to hear you guys because you guys should be able to share audio, but I am not hearing it. I apologize. I'm not sure what's happening here.
Can you hear
But
me, Dr. Simpson?
Marcel is in the session and he is very capable. So Marcel, if you want to take the question, you can go ahead and take the question. Let me know when you're ready to
Dr.
answer.
Simpson, can you hear me? You're not hearing us, Dr. Simpson. Guys, I'm going to point it out to her again. Hold on. Sorry for the technical difficulties.
Okay, I'm going to refresh my page to see if that will help with the audio issues.
All right, so Dr. Simpson is going to try and come again, but what was the question you guys had in the meantime? So when she come back, can somebody raise their hand
All
or
right,
something?
are you guys?
You can
Hello?
you can hear me now, Dr. Simpson?
Yes, I can hear you.
You
Sorry
can hear
about
me
that.
now?
Yeah, I can hear you.
Okay, so Peter Lindsay has a question, so I'm going to just come off so she can speak.
All right, awesome. Yes, I can go over the oxidation state of chromium 3 plus. All right. Is Lindsay, are you speaking? Because I'm not hearing anything anymore.
So, sorry, Dr. Stevenson, that was an error.
Oh, all right. So I'm guessing people want me to go over this example one more time. So let's go through it again. Okay. All right, so let's go back over the oxidation state for this chromium system. So again, the oxidation state of or the charge of the complex is going to be equal to the oxidation of the metal plus the charge of the ligands. So in this example, there is no counter ion. So what this tells us is that this is not a charged species. It's not a charge. It's not a charge. It's not a compound. It's a molecule. Similar to your organic chemistry molecules, such as methane or ethane, there's no charge to it, right? But if we were to pull off a hydrogen, we would get a charge then. Okay, so let's look at this example again. So if we look at this example, and this is a hard example, and you'll be getting a lot of these in your next tutorial. So we don't know what the oxidation state of chromium is. But in order to get to the oxidation state of chromium, we have to know what the oxidation state of our ligands are. So let's start from scratch. So let's start with the easiest one to do here are our chloride ligands. So we should know by now that chloride is going to have a negative one charge associated with it. So each one of these is going to be -1, right? The difficult one now is going to be the ethylene diamine ligand and the pyridine ligand. So from the beginning of the question, I said that pyridine is neutral, which means it does not have a charge. So we can think of it like ammonia. It's just zero charge. Ethylene diamine, each one of these NH2 is also zero charge. So they're not contributing to the charge of the molecule. So therefore, if you remember, the charge of the molecule, or the charge of the complex, is equal to oxidation state of the metal plus charge on ligands. In this example, we can see that the complex, there's no counter ion, there's no charge around it, therefore the overall charge must be 0. Right? Remember now that this is not NH, right? The overall charge here is 0. The oxidation state of the metal, we don't know, so we're going to call that X. The charge is on the ligand now, so we have to add all of those up. So we have chlorine -1, we have 3 chlorides, each of them -1. So that will be 3 times -1. Plus, the charge on pyridine is 0. Plus, the charge on the 1 nitrogen of ethylene diamine, that's 0. Plus, a charge on other ethylene diamine, that's also 0. Therefore, 0 is equal to X minus 3 plus a whole bunch of 0, which is equal to 0. So therefore, X is equal to +3. So the oxidation state of my chromium is chromium 3+. So once I have my oxidation state, I can now work out my d electron charge. So one way of doing it is to look at what group chromium is in. So if I look at the periodic table, I can see that chromium is in group 6. And if it's +3, it means it lost 3 electrons. So 6 minus 3 is 3. So therefore, this is going to be a D3 ion. So it's going to be chromium with 3 D electrons, right? The way we did it before was to look at the electron configuration of the neutral chromium atom, and we said chromium is Ar 3d5 4s1. If the oxidation state is 3, we would have lost 3 electrons, and that will still give us Ar3d3, and this is a Dr system, right? Yes, remember, we lose from the s orbital first, and then from the d, because s is our highest orbital. Okay. Thanks, Tia. All right, let's move on. All right. So if we go back to that complex, it's a bit more, there's more to it than meets the eyes. Because if I given you guys the formula and ask you guys to draw it, you might come up with two different structures. And I'm showing the two of them here on the screen. One with green chlorines and one with red chlorides, right? So the way in which I drew it the first time was to put the three chlorides 90 degrees apart from each other, right? So if I were to look at this as an octahedron, and I hope you guys remember the octahedrons you guys made for chemistry, the way in which I can look at a three-dimensional structure is that my chromium is going to be the middle of this octahedron, right? Up top, I'm going to have, so these two ligands on the very top, is the easiest one to see. I'm going to have NH2, right? And then this wedge here is telling me that the other NH2 is going to be to the back, right? So it's going to be here, right? So NH2 is the back over here. My pyridine is going to be here, which now means that my chlorides are going to be here. One chlorine here. And let's give them a different color. Let's make them green. It's a green chloride here, a green chloride here, and a green chloride here. So if I look at the arrangement of those chlorides, I will see that they actually occupy an entire face of an octahedron. And as such, we call this version of this isomer a facial isomer. So basically, if I gave you the same formula, there are two different ways in which you can arrange your chlorine atoms. In one case, they are all 90 degrees from each other, and that makes it takes up one whole face, and that becomes a facial isomer. The other way you could have chosen to draw this is now you have two of your chlorines, one 90 degrees from each other, and then two of them 180 degrees from each other. So if we went back to another octahedron and looked at how this would look, so in a three-dimensional space, again, chromium is in the middle, and we're going to have our NH2 up top, they're easy to see. We're going to have pyridine here. That's pretty easy to see. To the back, we're going to have another NH2 that's going to be over here in this corner, and then we're going to have a chloride here, and then another chloride here, another chloride here. And now if we look at the position of our chlorides in this molecule, you see that now they actually go across. They span the meridian of the molecule. And so when atoms or three atoms of the same type are in this arrangement, we call them meridional isomer or a mer isomer. So again, these two, so just looking at the formula, we could draw these in two different ways. That means that they have the same molecular formula but different structures, so therefore we have isomers. And if we have a system with three unique atoms, such as this one, we have three chlorides, they can either occupy the face of my octahedron to give me a facial isomer, or they can line the plane to give me a meridional isomer. All right. So with that, we're going to go into isomerism. So it's now 6 o'clock, which means it's time is up for the lecture. Do you guys want to go some more, or should we continue this next week? Oh boy. Some people have class. So to continue. All right, so let's go into isomers fully next week. The slides are on our VLE, and you'll see that there are some blank ones. So maybe what's a good thing to do would be if you guys or you want to do a poll. All right, let's see. But if people really can't, because it's not equitable for me to continue a class that they won't be able to take part in. So what I will do is that we have office hours tomorrow, so we can continue then. It's good to see some of you guys want to continue. I'm sorry about the audio issues. That did rob us of some time, but it's gonna be neck and neck, like I'm at the horse races. But again, the slides are up. I'm gonna keep this format. I learned to do better at writing, but you can print off the slides, and as I go, you can make your own notes on them, and you can use them as worksheets as we go along. And there are also questions and stuff, and we'll try to see if we can make the best of platform. All right, I'm seeing that there are people. If you have a question, go ahead and just talk. So we have more. All right, you guys can talk. If I'm not hearing you, let me know so I can refresh my browser again. All right, I'll just show one more slide and we'll call it a day, because isomers is going to take a lot. And the yes have a slight advantage, but there are lots of people who haven't responded. All right, so seeing as not overwhelming yes, we're going to go one more slide. So we're going next week is we're going to look at isomers. Right. We're going to look up isomers, and we're going to look at what they are, and we're also going to describe the type of isomers that we have in coordination compounds. So it's mainly a lot of definition, and it's going to be a lot of definitions and structure. Again, the slides are up. More detailed slides and more detailed notations are also up, but these are blank. I'll be back here tomorrow at 8 a.m. So for those of you who want to have questions, I'll be here again Thursday 3 to 5, and then next class we'll jump right into isomers and talk more about coordination compounds and bonding. Have a good one. Please be safe out there, and all right, later guys. Bye.